Alrighty guys, let's go ahead and take a look at two-dimensional forces here. So really the big idea here is that when you push an object or when you pull an object and when you apply a force to it, the only force that's actually going to do anything to changing the motion, which again a change in motion is an acceleration. If you want to change its motion by applying a force, the only force that is actually aiding that change in motion is the one that is in the direction of motion, which is also known as the one that's parallel. If it's parallel, think parallel lines, right? They're running in the exact same direction, in the exact same plane. So by going parallel here, what that tells us is that these forces are going in the exact same direction as the motion itself. So looking at the two diagrams on the slides here, the top one being one that's not broken down into the individual components. What this one would be, this would be an object being pulled, likely pulled to the right at some angle above zero. There's weight, so we've got mg, remember mass times gravity for our weight. We've got our normal force, and then we've got friction resisting our motion backwards to the left. Now the diagram on the bottom has a breakdown of the individual components. Remember back to our last unit on two-dimensional motion, where those components are just the individual aspects of that force. So our overall force, F, is going to be at some angle. F cosine theta and F sine theta. Cosine and sine are going to be our horizontal and our vertical components respectively. If you look at where that angle is coming from, that angle is being referenced from horizontal. So cosine theta is going to get us f of x, and sine theta will then get us f sub y. So looking at what those vectors look like, being able to use some trig here, this is ultimately what we have. We've got some force pulling at an angle, so that's going to be F, that's going to be our overall force. So if that force is pulling at an angle, drawing out our vectors here, just like we did with two-dimensional motion, F sub x gives us our horizontal component of force. F sub y then gives us our vertical component of force. Just like it says on there, if we want to find with respect to this interior angle here, cosine is going to get us f of x, sine is going to get us f of y, because here we have our adjacent side, here we have our opposite side. Typically, but not always, we're going to be given this overall force. Looking at this in perspective here, some component of this force is not going to be in the direction of motion. For example, if this object is moving horizontally, this is the component f of x that is going to be applying the actual force that's causing the change in motion. Whereas f of y, in that case, would not be aiding in that change in motion. If anything, it would be alleviating some of the vertical forces, such as the weight, that are pulling down on it. If we want to look at a quick example of where we could use this. So let's say we have some object right here. Let's say we've got some object, and this object has weight. So it's got F of some weight there on a surface. So we're going to have a normal force that is equal and opposite. We're going to assume no friction for right now. We're going to go ahead and assume no friction for right now. And let's say that this object is being pulled with some applied force. Let's say this overall force here is 50 newtons. Let's say we've got an overall force of 50 newtons here. But if we give a little more detail here, because at this point we don't necessarily know which component we'd want to look at, the horizontal or the vertical, so f of x or f of y. If we add a little disclaimer here that says this object is moving to the right, which hopefully with the lack of friction you'd be able to determine there. That means we've got two ways that we can then look at this, right? We're going to look at what is our horizontal component. we can find our vertical component f of y, but that's not necessarily going to give us any substantial information in this scenario here because we're moving to the right. The force in the direction of motion, so the parallel component, is the one that we're looking for. Just to give some more numbers here, to give some context, let's go ahead and say that our interior angle theta here, let's say that this is 35 degrees. Let's say that that's 35 degrees. So what we would have to do here, if we want to find, hey, what is the horizontal force in the direction of motion, what we would be looking at here is, again, a cosine function. So cosine of our angle theta, cosine is your adjacent. Our adjacent side here is f of x. Our hypotenuse is the overall force F. So if we want to then sub in our variables, we'd be looking at the cosine of 35 degrees equals f of x, the horizontal component, over our overall force, which is 50 newtons. So we go ahead and multiply this over here. We get our horizontal component, f of x, equals 50 newtons times the cosine of 35 degrees. And if you notice, this is the exact same formula that's written in that bottom right diagram on the slide here. This is the exact same one that's written in the bottom right on the diagram. So going through this here, just to go ahead and get a number for you, 50 times the cosine of 35, this gives us a horizontal force of approximately 41 newtons. We're going to be, for the sake of sig figs, and so you guys don't get me for this one here, we're going to go ahead and call it 2 sig figs apiece. Right, so we're at 41 newtons for a horizontal force. Finding the vertical force would be much the same process, except now we've got 2 side lengths, so we could use Pythagorean theorem to get f of y. Or, rather than using cosine of 35, we could use sine of 35. You've got enough information here, you should be able to do that trig to find f of y. So that's our f of x. Now, to put a little more context into it, let's add one more force. Let's add friction. And because this is moving, we're going to go ahead and call this our kinetic friction force, F of K. And let's say that F of K is pulling back with 19 newtons worth of force. Let's say that's pulling back at 19 newtons worth of force. And if I were to say, what is the net force that is acting? Because we've got 41 newtons to the right, F of x. We've got 19 newtons working to the left at 19. Our net force in this case, so if we're to find that net force, we would be 41 newtons going to 41. We would be 41 newtons going to the right. We would be 19 newtons going in the opposite direction. So that would then give us a net force. If you go ahead and do that math right there, that would be 22 newtons worth of net force. So that's how we're going to go ahead and find this. So just by adding this little angle in here, all that we've done is changed it from only being in the direction of motion to now, based on the angle, we're only using a component, we're using a part, we're using some of the overall force that we're pushing or pulling with. Usually this only applies to an applied force. Let's go ahead and take a look back in the lab here. We'll transition back. I'm going to show you guys what this looks like back in the lab. Alrighty, welcome back to the lab part of this video lesson here. Now what we're looking at, we got a friction block. It's got 1,000 grams, so 1 kilogram worth of mass within it. All that I'm going to do back here is show you guys what happens when we apply the force parallel to motion, when we apply it at an angle pulling, and when we apply it at an angle pushing, just so you guys can see some of the differences here. Now, first one right away is just applying this motion horizontal, so in the direction of motion. And what we're going to notice is that this force sensor is going to read and read and then eventually start to move, where all that it takes is a little over 4.5 newtons to keep this moving at a constant rate. Now go back and look at that static friction max. The static friction max here is going to be just a shade over 6, with the kinetic friction force again being much lower. If we look at what happens when we pull this up at an angle, right, so now we're trying to move it horizontally, but we're pulling at an angle. This overall force is going to peak out at just over 6, but now look at that kinetic force. It maintains at just over 5. Last idea that we can look at here is actually pushing down, right? So pushing down versus pulling at an angle. So all we're going to do is change the direction. Now the sensor is going to read negative. That's just because it's pressing in the opposite direction. So if we go ahead and press here, look at how large these forces are going to get before we even see any sort of movement. Right, we're getting up into the 12, 13, 16, 18 Newton range. And then to maintain that state of motion, we're talking somewhere around 10, 12-ish newtons or so. Reason behind that, so if we think about the difference between pushing and pulling, if you push down here, your vertical component of your force is pressing into the ground, which is making this contact point between the two surfaces seem heavier than it really is, because your vertical component is being added downward, so it's increasing the apparent weight of the object, which is going to increase the frictional force that we have. Versus when you pull up on it, your vertical force is now counteracting the weight, so it's going to give it the appearance that it's lighter than it actually is. Looking at it, these are the ways that we look at our two-dimensional forces. So you should be able to apply these forces at angles and understand what the net force actually is based on the different components that we have. If you guys have any questions, obviously make sure you let me know.